3.6, we're going to look at polynomial and rational inequalities. So we're going to start with the polynomial inequalities. And so the first ones we're going to look at are going to kind of look like this, and then we're going to get to some with a little bit higher order. So what we want to do here, I kind of have a step-by-step process on how to do this. And I also have a graph. You're not always going to have a graph on these, but on the first example, I kind of like to show graphs so you can see the visual on this. So right here, solve each polynomial inequality, graph the solution set on the real number line, and then express the solution in interval notation. So here kind of are the steps for this. So find the x-intercepts and test the values between and beyond any x-intercepts. If the tested value within a subinterval satisfies the inequality, then all the values within the subinterval satisfy the inequality. So what's going on here is basically, if you were to look at this right here, this is basically x minus 5 times x minus 2 equal to y. If you were to kind of think about the parabola here, I put equal and I put a y here just for a moment. So you can kind of see if you were to graph this, this is what you would get right here. Now, we don't actually have a y and we don't have an equal sign. What we're saying instead is we want whatever values I plug in for x, um, it needs to be greater than or equal to 0. And so what we're trying to do is we're trying to figure out x values that when I plug them in return, my y value will be greater than or, I'm sorry, in this case, just greater than 0, not equal to, greater than 0. So that's what we're trying to figure out. What x values will give me a y value? Because this is, maybe I should write it like this. This might make a little bit more sense. I'm going to put the y equals right here. So see, I'm trying to figure out when the y is greater than 0, right? So I plug in my x value, and then that's going to give me a return value, my y value. And so my y value needs to be greater than 0. So you can see on the graph, this is where y is greater than 0. So I already know that that's going to be my solution set right there. But like I said, we're not always going to have a picture. And so really the easiest thing to do is what I have in the instructions. Just find the x-intercepts and then test between and beyond. So let me show you that real quick. So for this particular example, my x-intercepts would be at positive 5 and at positive 2, right? Those are the two values that will cause this to equal 0, right? And we call those, a lot of times we'll call them the boundary points because my results will change from being positive to negative or from negative back to positive. Now be aware, sometimes it can bounce off the x-axis, so sometimes there is not a sign change when you have an x-intercept, and we'll probably run into a couple of those cases later. Okay, so back to the process. What you want to do is find the x-intercepts. Bingo. Then put them on your number line in numerical order. So I'm going to put the 2 here, and I'm going to put the 5 here. And then see if those x-intercepts are part of the solution set. Well, if I were to let x equal 5 or 2, what would happen is I'd end up with this statement here. 0 is greater than 0, right? Because this would go to 0. If I plug in 5 or 2, I'm going to get 0 in return. Is 0 greater than 0? That is false, right? That's false. So I'm going to put an open circle here and here, okay? Because those are definitely not solutions. But now what we have to do is test a value between and beyond any x-intercepts we have. And if it's true for one of those values in that subinterval, then it's going to be true for all of them. So basically, I'm going to test a point here between negative infinity and 2, then a point between 2 and 5, and then from 5 to positive infinity. So my first point over here, I probably want to try 0. 0 is always an easy one to test. So I'm going to let x equal 0. And so if I do that, once again, I don't have a lot of room for my algebra here, so I'm going to just kind of do this in my head. 0 minus 5 would be what? Negative 5. And then 0 minus 2 would be a negative 2. And then this is a question, is that greater than 0? Well, a negative times a negative is positive, And so yes, 10 is greater than 0. So that's going to come back as true. So that means that 0 is a solution to my inequality. But what that also means is everything between my x-intercept and the next x-intercept, which I don't have one, to the left, is going to be part of my solution set. So everything from negative infinity to 2 is part of my solution set. And so since I don't include 2, I have to put the parentheses right there. Okay, next I need to test a point somewhere between my x-intercepts, so somewhere between 2 and 5. You could test 3 or 4. Let's kind of keep the number small. Let's go with 3. So once again, I'm going to plug 3 in right here. 3 minus 5 is going to be negative 2. And then 3 minus 2, which is going to be positive 1. And then is that greater than 0? Is that greater than 0? So negative 2 is greater than 0. Let's see, negative numbers greater? No, that's going to be false. Negative 2 is not greater than 0. So you do not want to shade this part right here. You don't want to shade between 2 and 5. And then we got to test one more. And so let's see, let's just go with 6. So we're going to plug in 6. So back up here, 6 take away 5 is 1. And then 6 take away 2 is 4. And then greater than 0. Well, let's see, 1 times 4 is 4. Is 4 greater than 0? Yes, true. 4 is greater than 0. So we'll go ahead and shade this part of this. So now on my interval notation, I need to union and then go from 5 to infinity right there. So 5 to infinity. And once again, I have the picture here on the left. Okay. So what you want to do, find x-intercepts, and this will be a common theme you'll see on other examples aside from these. Find the x-intercepts, then test between and beyond any x-intercepts you have. All right, let's try another one down here. So what's going to be different about this one is I have to factor it. It's not ready yet, so I got to factor this. So let's see. This is going to factor into x plus 8 and x minus 3. Or no, I'm sorry. Okay. Yes. Okay. I have a little typo here. I thought I had fixed this, but I guess not. Let's change that to a minus 18. And that should kind of fix our issue for us. And then, yes, oh, I gotta change these signs. Okay. So let's see, we'll put this as a minus 6 and a plus 3. Sorry about that. I thought I'd fix that, but I guess not. All right. So now what we're going to do is continue to find those x-intercepts. So my x-intercepts are going to be at positive 6 and at negative 3. Okay, and so put those on the number line in numerical order. And then ask yourself, are my x-intercepts part of my solution? Right? Because if you plug those in, this will go to 0 right here. And so ask yourself, is 0 less than or equal to 0? And yes, that's true. So those values on here, we're actually going to include them. So I'm going to put closed circles on here. Okay. And so now it's time to test between and beyond. And so I just kind of like to go from left to right. So I'm going to start over here. And so let's start with like negative 4 would be fine. And so you can plug it into the original if you want. It's going to be easier if you plug it into the factored form. It's going to go a lot faster. So negative 4 minus 6 is negative 10. Then negative 4 plus 3 is a negative 1. Is that less than or equal to 0? Well, let's see. That gives us positive 10 is less than or equal to 0. Well, positive numbers are not less than 0, so that is false. So you do not want to shade in this part right here. So we're not going to shade here. Next, let's see. 0 is available. So if 0 is available, that's always an easy one to plug in. So let's see. 0 take away 6 is negative 6. And then 0 plus 3 is 3. Is that less than or equal to 0? Well, we're going to get negative 18 is less than or equal to 0. Negative, yep, any negative number is less than 0, so that's going to come back as true. So we're going to shade between there. So I'm going to go ahead and add that to my interval notation. So from -3 to 6 is going to be part of my solution set. And then let's see, now I need to test, let's test 7. 7 is beyond that one right there. All right, so what we're going to do here is, let's see, 7 take away 6 is going to be a 1. 7 plus 3 is going to be 10. Is that less than or equal to 0? 10 is less than or equal to 0. 10, nope. Got the same one we had on the first one we were trying, so that's false. So we don't want to shade there. So it was just in between this time. Okay, so you might be kind of picking up on a pattern that seems like it will go false, true, false, true, true, false, true, that kind of thing. Yes, that is typical, but not always the case. It can go false, false, or true, true. So you just be aware of that. Okay, I think I've got one more of this type right here. Okay, and so the only difference on this one is when we get started, you do want to go ahead and one side needs to be 0. So I'm going to subtract 10x and add 24 to both sides. So subtract 10x and add 24. And so I need to line them up in order. So the x squared goes first, then the minus 10x, then the plus 24 is less than 0. And then we want to go ahead and factor this. And so let's see what multiplies to give me 24, but add up to -10. It should be a -6 and a -4, right? Does that seem right? Negative times a negative is positive. Yep, adds up to that. Looks good. So my x-intercepts for this one are going to be at 6 and 4. Okay, and then are those intercepts part of my solution set? And the answer will be false, because when you plug them in, you're going to have zeros less than 0, which is false. So that these x-intercepts, they're important. They're a big part of what I'm about to do here, but they are not included as part of my solution set. So I put open circles on them. And so then now I need to test something between 4 and -infinity, which the easiest thing would probably be 0. And then between 4 and 6, the easiest thing would probably be 5, unless you want to deal with a decimal. And then something greater than 6, which would be like a 7. Okay, so once again, I would plug them into the factored form. If you really wanted to, you could plug them into any one of these forms, but this is going to be the easiest one. So we're just going to plug it in right there for x. So when I plug in 0, I'm going to get -6 times -4 is less than 0. And so we're testing it. And so let's see, we're going to end up with positive 24 is less than 0. That is a false statement. Positive numbers are not less than 0, so that's going to be false. So we don't want to shade that. Then let's see, in the middle, we're going to try 5. Let's see, 5 take away 6 is -1. 5 take away 4 is +1. Is that less than 0? And in this case, yes, -1 is less than 0. That's going to come back as true. So we want to shade between. And so that's going to be everything between 4 and 6, but not including our ends. So we have to put the parentheses there to indicate that everything between, but not including the actual 4 and 6. Okay, so then now we need to test 7. So 7 take away 6 is 1. 7 take away 4 is 3. Is that less than 0? Is 3 less than 0? No. 3 is not less than 0, so it's going to be false. And so, anyway, so the pattern did hold here. False, true, false. Like I said, that is going to be the pattern for the most part, but you can't assume that. We will run into a couple of cases where we'll get a false, false, or a true, true. So just kind of be aware of that. And so that's going to kind of wrap up the first part. What we're going to do next in the part 2 videos, we'll look at the higher ordered polynomials. We'll go above powers of 2. And so there we go.